A function is a rule that connects one set of numbers to another set of numbers. There's a relation between the inputs and the outputs of a function. Here we have an example of a function denoted by f of x, and that is you put a number x in, a value for x goes in, you add 2, then you square the result, then you take away 1, and it gives you the output. Now each input is related to exactly one output. For example, here if 0 goes in, 0 plus 2 is 2, square it you get 4, take away 1, and 3 would be the output. If we put negative 4 in, then negative 4 plus 2 is negative 2, square it you get 4, take away 1 you get 3. Now that's allowed in a function because each input is related to exactly one output. This case here with the squaring, this is called a many-to-one function. But you cannot have a one-to-many function. And we'll talk more about that later. Let's go back to this then. The input, what we're allowed to put in our function, has a special name. That's called the domain of the function. So the numbers that you can put in is called the domain, and the numbers that come out, the output, that's called the range. Let's have a look at this function in more detail. There it is again, f of x equals the square of x plus 2, take away 1. Now let's say we restrict the domain, so we're going to use D for domain, and we're going to say that the only numbers you can put in are, we'll go square bracket, which means it includes the number I'm going to write here, which is negative 2, and it's allowed to go up to infinity, and we'll put a round bracket there because that's a limit. The limit of this is infinity. Remember, infinity is a limit, not a number. I could have expressed this as the values of x are all greater than or equal to negative 2. Well, if that's the domain, if they're the numbers that can go into the function, what is the range? Well, the range is what comes out. So if we put negative 2 in here, we get negative 2 plus 2 is 0. Square it, you still got 0. Take away 1. So negative 1 will come out. So we'll put a negative 1 as the lower limit of this. How do I know that that's the lowest one? Well, when you square something, it's always greater than or equal to 0. It's always positive apart from when it is 0. So the greatest this bit can be is 0, and then you take away 1. So we know that the lower limit of that is negative 1. We put a comma. If we put a really big number in here, we add 2 to it, we square it, we take away 1, we get a really big number out. So the limit for the range is also infinity. And that's the output. So we've got domain and we've got output. Let's find an expression for the inverse of this function. So in other words, we're going to put in the range and get out the domain. So these are going to switch around. To find the inverse, we will say let y equal f of x. So now we have y equals the square of x plus 2, take away 1. And what we want to do is change the subject of this equation. So instead of y equals, we want x equals. So we'll do y plus 1 is equal to the square of x plus 2. And now we're going to square root. Let's move the page up there. We square root both sides, so we have the square root of y plus 1 equals x plus 2. But as we know, a square root has two possible answers, plus or the negative. And this fits in with what we said earlier about the square root being a one-to-many relationship. Well, it's currently not a function because of this. You cannot have a one-to-many relationship for it to be a function. So we're going to have to deal with this. And the way we deal with that is to consider, once we've moved this over, let's do that now, y plus 1 take away 2 equals x. And of course you've got the square root there still. So we need to consider what's going on. Now I said we want the, looking back at the original function, the range of the inverse function is the same as the domain of the function. The range of the inverse function is the same as the domain of the function. So all we're getting out of our square root are any values from -2 to infinity. So it makes sense for our square root to be positive. This has to be a positive square root for that to exist. The lowest this is going to be is 0, and then we take away 2. That's where we're going to get this range, because everything else is greater than -2. So we need to choose the positive square root. We must show that we've considered both possibilities. That's why I've got a plus and a minus. But we choose the positive so that the range of the inverse matches the domain of the original function. So our final answer, we say the inverse, that's the -1 up here of x, the inverse function of x equals the square root of, and we're going to substitute x for y. So we've got x plus 1 square root, and we're not writing the plus or minus this time, we're leaving it as a positive because that's what we've decided. There we go. And the domain of the inverse is equal to the range of the original function, so that's -1 to infinity. And the range of the inverse is equal to the domain of the function, so that is square bracket -2 to infinity. Here we have the original function and the inverse function. The graph of the inverse function is obtained by reflecting the graph of the original function, that's the graph of f of x, in the line y equals x. Now the first thing to note is the domain of the function has been restricted, and that's so that the inverse exists. For the inverse to exist, there has to be a one-to-one relationship between the input and the output, between the domain and the range. So that's what we've got here. Now, when x is -2, we get an output of -1. So we've got this point here, and that's the start of our graph. And we know that it's a U shape, but we haven't got the other side of it because the domain's been restricted. We could work out that when x is 0, like we did earlier, the output is 3. So we've got another point we consider there at 3. So if we just do a quick sketch of this graph, we get a sort of Nike tick effect, don't we? So we're coming down here and we want to go up like that through that point there, and then it will continue up there. Now, it's only a sketch, don't worry, it's not perfect. There's the 0 point there. So now if we draw in the line y equals x, so that's coming through my graph like this, y equals x. And remember that the graph of the inverse is a reflection of the original graph in the line y equals x. So we can see these points here. We're going to have this, this point here, and we're going to have this point here. So the graph is coming up like this, through there and around there, just like that. And it should be a reflection of one and the other. I could have noticed that it's gone through -1 here. I could have found that out actually by letting this graph equal 0, and I'd have 1 on this side. The square root of 1 is still 1, and then we'd have 1 is x plus 2, and that would give me one result, and then -1 is x plus 2, and that would give me the other result. The final thing to do, of course, is to label each graph. This one was y equals f of x, and this one is y is the inverse function of x. There we go. Here we have two new functions, g of x that has a domain of negative infinity to infinity, and h of x which has a domain of 0 to infinity. And we want to find this composite function g h of x, which is where the input x has the function h applied to it, and then once that's done with, g gets applied to it as well. The first thing we're going to look at are the ranges of these two functions themselves. So the range of g of x, if you put a negative infinity in for the value of x, you get really close to 0. And if you put a large number in for this, you get a large number out. So the range for g of x is 0 to infinity. Let's look at this one here. When you put 0 in, or a really small number for the ln of 2x, you get a large negative. And when you put a large number in, you get a large number out. So we've got the corresponding ranges and domains for each function. Now let's go back to this composite function. For this to exist, the range of h of x, that's what comes out after applying the function h. The range of h of x has to be contained within the domain of g of x. G of x has to be able to welcome all the outputs of h of x. Otherwise the function can't exist. Well, let's have a look then. Does the range of h of x fit into the domain of g of x? Yes, it does. So we know this function exists, but what is it, and what are the domain and the range of this function? Well, we can look at the domain and range of this composite function just by considering these. So the domain of gh of x is the domain of h of x. So we got that straight away, 0 to infinity. The range takes a little bit of thought. So we've put these numbers in, we've got these numbers out, negative infinity to infinity. These then go into g of x. And because these match, we then get the range of g just so happens to match the range of g of x. But we have to make sure that we've considered the range going into the first function here, this g of x function. So in this case, it's worked out nicely. Our range is also 0 to infinity. But what is the function? So we're going to take h of x, which is the output bit we got here, ln of 2x, and we're going to put that as the input of g of x. So let's just do that here. G h of x equals, we've got 2e to the 3, and then we're going to put the ln 2x for x. Remember, the output, which is represented by ln 2x, becomes the input of g of x. So where we see x here, we write ln of 2x. So that's our composite function, but it could be tidied up a little bit. So g h of x equals, what can we do here? Well, we've got some logs going on here. So this is n log x, and n log x is equal to the log of x to the n, so we can cube this, and then these two are opposite, they're the inverse, one is the inverse of the other. So g h of x is 2 lots of this, 2x cubed. So g h of x, our composite function, is 2 lots of 2 cubed is 8, and x cubed we can write as x cubed. So final answer, gh of x equals 16x cubed. And actually we could check our range for this, couldn't we? So the domain of gh of x is the same as the domain of h of x. So 0 to infinity. If you put 0 in here, we get 0 out. If we put infinity, if you put a large number in here, we get a large number out. So this agrees with what we said earlier. So another method to find these two things is to find the composite function first and then put the domain of h of x in, and that will give you the range of gh of x. One final step. Sometimes you might get asked a little bit of a further question to solve an equation. So it could say solve the equation gh of x equals 128, and so we're just going to let this equal 128. By simplifying it, you can see how much easier that is now. So 16x cubed equals 128, which means that x cubed is 128 divided by 16, which is 8. So x is the cube root of 8, which is 2.